Okay, chal, start. Good morning. So last class we saw about pipelining, and so this was the figure where we stopped with respect to pipelining. So what we see here is that 5 instructions can be executed concurrently, and each instruction is in a different stage of the execution of the instruction. So there are 5 stages as we have seen here. So every instruction is in a different stage. Now the question remains, there are 2 questions here. Now question number 1 is it possible to have such a free flow? Is there something that will hinder? Question number 2 is that will every execution take the same time? For example, we have seen floating point addition, floating point multiplication, to a large extent our Wallace tree multiplier addition, they all take almost same time, but there are operations like square root of a floating point number, sin x, cos x, there are some lot of functions that are implemented. Division, for example, will take much more time than a normal operation. So the assumption that every instruction will take the same time is incorrect. So that is also something that we need to keep in mind. Keeping all these things in mind, what we will now do is that we will see how to go away from this ideal case, right. The ideal case is that the instructions can flow. What are the things that can stop a free flow of instruction? What are the things that could stop I2 to flow immediately after I1? Is there some conditions which will stop IK to immediately follow IK minus 1, right. So we will look at those details and finally come out with what we call as the superscalar architecture. Okay. So how to build a superscalar architecture, what is inside a superscalar architecture is what we will finally see. Now before going forward, right, why do we call some architecture as superscalar? What do you mean by superscalar there? Now we will see this architecture can also do more than one instruction per cycle. Okay. So the cycles per instruction, CPI we call, okay, cycle per instruction is less than 1. Number of cycles, average number of cycles I spend per instruction, if it is less than 1, then that means I am a superscalar architecture. What you see here is that every instruction, 1 unit I finish 1 instruction, right. So what you see in pipelining, in 10,000 the 10,000th instruction comes at 10,004 unit, the first instruction finishes 5th unit, second instruction is 6th unit, and so on. So every unit I get 1 instruction. What is that unit? Basically cycle, right. Every cycle I get 1 instruction. So cycle per instruction is 1. This is not superscalar. Can I get something like CPI is less than 1? Then you become a superscalar architecture. So that means what? There should be multiple issues, we will come to that. So how do we build such an architecture, and that is very important for you to understand, because modern architectures today are superscalar architectures, right. So let us go. So we all saw these slides that day. Now we will go to now ILP is called instruction level parallelism. Pipelining is an example of instruction level parallelism because I execute more than 1 instruction at the same point of time. That is why we call it instruction level parallelism. Now let us see what will happen that will hinder the free flow of instructions, right, and that is what we need to address now. Let us take these 2 instructions, okay. Load, there is a small variation in syntax, load R2 plus 10 comma R1, that means the content of R2 plus 10 is loaded into R1, right. We will have a small change in syntax, that is okay. So R1 gets the content of load R2 plus 10. So from memory I am loading into a register. Now what add does? It reads the value of R1 and R2, then it sees R3. Okay. Now unless load completes, I cannot fetch the data. Please note, let us go back to our pipelining here. before the previous instruction finishes execution, I cannot fetch the data for the next instruction. Before the previous instruction finishes, that is when the previous instruction stores back the value into R3, then only, or R2, then only the fetch data of the next instruction can happen. So, the next instruction cannot follow the previous instruction because there is some dependency. This dependency is called a hazard. Okay. Now, we will go and look at this hazard in a. Now, what happens here? Now, I see R1 is being written here, written into, and unless it finishes the writing, I can't read that value. If I read the value before this finishes writing, I will get some previous value of R1, and that is incorrect. When I am executing the program one after another, this add needs this value of R1. So, I cannot fetch the data for this add unless this instruction finishes execution. Are you able to understand this? So, if this is I1 and this is I2, this I2 cannot follow I1. The I2 will be fetched, it will be decoded, then I have to wait for I1 to go and finish the results, store back the results, then only I can fetch the data for this. So, 2 cycles, this pipeline is stalled, STALLED. Okay. This stalling is because there is a hazard, there is something undesirable, that is why I call it as an hazard. And this hazard is because of what? This hazard is because of data, right. That fellow is going to dump some data which I need. Since that fellow has not finished storing that data, I cannot fetch the data because the latest data is in the hands of the previous instruction, correct. So, I am stalling this pipeline because there is a data dependency, hence this hazard is called a data, followed, yes or no. Now, this hazard is also called read after write hazard. I am reading, add is reading, after load wrote into this, right. So, this hazard is also called as raw hazard or read after write hazard, followed, okay. Now, there will be other type of hazards, we will see as we proceed, okay. So, this is read after write hazard. Now, let us see what is happening here. R1, let us take the next example. R1 is written, R1 is read, R3 is written, R12 is read, okay, 3 things. R1 is read, R3 is written and R12 is read. Here again R1 is written. Here again R1 is read, R2 is read, R12 is written. Okay. You are seeing this. Now, between 1 and 2, there is a read after write hazard because R1 is read and R1 is written. So, there is a read after write hazard between 1 and 2. Let me call it I1, I2, I3. Between 3 and 1, please note that there is something called write after write hazard. Why is this a problem? Right? If I have, what I mean by write after write hazard, for some reason, since I am now what I want to have superscalar architecture, that means more than one instruction should finish at the same point of time. When I am constructing such an architecture, what happens if I3 finishes before I1, I4 is going to follow I3, I1, what will I4 get is the value of I1 and not the value of I3, right. So, when I start executing more than one instruction in parallel, right, then what happens, I have to have some control over how the instructions complete, because I allow all the instructions to execute. Some reason we will come out how why that possibility can be. If I3 finishes before I1 and then I1 finishes last, I4 will get I1's R1 and not I3's R1. You got this? So that is why we call it as a write after write, because I1 is also writing, I3 is also writing, we call it as a write after write hazard. Similarly, there is also a write after read hazard between I2 and I4, because R12 is read here while R12 is written here. So a write after read, okay. There is a write after read here. R12 is read here while R12 is written here. Why again this is a problem? Because if I4 finishes before I2 or I4 finishes before I2 starts executing, because anything we are introducing parallelism here, and I4 finishes before I2, then what happens? I2 will get the R12 of I4, but I2 should get the R12 of some instruction before it. You are getting this? So the moment I go and say that I will now start, I want a superscalar architecture where the number of instructions I finish at a single cycle is less than 1. That means I am pumping more instructions into the system, and when I pump more instructions into the system, then what will happen? All these instructions can start executing concurrently, and there can be some who finishes first and who finishes last. I do not have a control over. If I do not have proper control, then what will happen? I will land up with these type of data hazards, and the data hazards are read after write, write after write, write after read. If I have a normal pipeline, that is one instruction after another instruction, I do not want a superscalar, then the only problem that will come is read after write. But if I have a superscalar pipeline, then I could have read after write, write after write and write after read, all the three possible data hazards. Are you able to follow? Yes or no? Okay. Now we will take the superscalar architecture construction and show how these hazards can come and how the architecture handles it, right? How the architecture itself handles it. So the compiler can be dumb. Compiler need not take care of all these hazards, okay. The compiler just compiles and leaves it. It just gives a sequential program. The architecture, there is lot of hardware that is built inside the architecture which shall take care of all these data dependencies, okay. What is that architecture? How can we build one? These are things that we are going to discuss. Are you able to follow? Okay, fair enough. Okay, good. Now, so this is our architecture. We want to build a superscalar architecture, so CPI should be less than 1. I want CPI should be less than 1 here, and the main issue here is that I can fetch more than one instruction at the same time. I can decode more than one instruction at the same time. I can go and fetch data for more than one instruction at the same time. All this I can do. Then I will go and execute. I will have multiple execution unit. Instead of one adder, I will have 4 adders, correct. Instead of one multiplier, I would have 5 multipliers. So I will have multiple execution units. So multiple instructions can execute at the same time, and multiple instructions can store back their data at the same time. If I am going to enable all these things, then I can achieve this CPI less than 1, okay. And the more important thing is different instructions will take different amount of cycles to complete. So then I can basically make each one of these execution units as pipeline, so that I could pump more and more data as and when it comes. So this is also very interesting part that for example, I can do 4 floating point multiplication while 1 floating point division occurs, and that is where you will land up with what we call as the out of order execution. So suppose I have 1 floating point division followed by 4 floating point multiplications. So, I have two floating point units, let me say FPU1 and FPU2 are two floating point units. Then what will happen? The FD will start executing here, it will take say 40 cycles for example, while the FMUL which is following, let me say this is I1, I2, I3, I4, I5, your I2 will come and start executing, it will finish off in 4 cycles. So, actually I2 completes before I1, right. I2 actually completes before I1 completes. Then I3 will start executing, it will also conclude it will also complete before I1 completes. I4 will start executing, it will also complete before I1, and I5 and I1 will complete. So, there are at least I2, I3, I4 3 instructions which completed before I1 completes, right. So, in that essence we are doing what we call as out of order execution. Out of which order? There is an order given by the compiler. What did the compiler do? It gave one FD which we call it as I1 followed by I2, I3, I4, I5, those are all floating point multipliers, multiplication instructions. Now what has happened here? FDIV starts executing, it takes 40 cycles. Before FDIV could complete its execution, which was I1 completes its execution, I2 completed, I3 completed, I4 completed, and I5 also completed when the I1 completed. So essentially it is not that the previous instruction completes and then the next instruction completes and then. So the way I am executing is basically out of order. Which order? Out of order of the order that was actually given by the compiler. Okay, you are able to follow? So this type of an architecture, this type of an architecture can basically get this superscalar behavior. So if you want a superscalar behavior, we need this type of a pipeline environment. Is it fine? So what are the difficulties in the superscalars construction? Difficulty 1 is that I have to ensure no data hazards. Okay, there will be several instructions that are executing. I have to see that there are no data hazards, meaning if there are data hazards I need to handle. Okay. Now what I mean by handling data hazard, I will say, oh, if I1, I2 depends upon I1, then I will say I2, I just keep I2 waiting till I1 finishes. So let me say I1, I2, I3, I4, I1 depends upon I1, I2 depends upon I1, while I3 and I4 are independent. I now say I allow I1 to execute and then I3 and I4 to execute while I2 will be still waiting for I1, right. So this is why I again say this is out of order execution, because I3 executes even before I2 is executed, because I2 is waiting for I1's result, while I3 and I4 does not have any dependency, it can start executing. That is how I am getting superscalar process, that we have explained. Now the point is, the hardware basically says I1 now you go and execute, I2 you wait, I3 now you can execute, I4 you can execute. So what it means, this hardware is responsible for allowing an instruction to execute or stopping an instruction from not executing. So the hardware does instruction scheduling. What do you mean by scheduling? Scheduling a class means this class will happen at this point of time. Scheduling an instruction means this instruction will execute at this point of time. Are you able to understand what I am saying? So what is it? What is the hardware doing? It now schedules the instruction. When it is scheduling the instruction, when the process, when it is a process, when the program is in execution, it does the scheduling. That is why we call it as dynamic instruction scheduling. This entire process is called dynamic instruction scheduling, because this happens when the program is in execution. The hardware sees 5 or 6 instructions coming. Now it analyzes the dependency between these instructions. Dependent instructions, it makes them wait. Independent instructions it allows to execute. And all these things are done by the hardware. The compiler need not care anything about it. And so this is this type of an instruction scheduling, since it is done by the hardware at the time of execution, this is called dynamic instruction scheduling. Are you able to follow? Any doubts in this? Now the other aspect is that this is compiler's heaven. Compiler does not bother about the architecture. The other aspect is that if the compiler does this scheduling, so compiler sees 10, it groups, takes 10 instructions, it analyzes whether there are dependencies. If there are no dependencies, then it allows, it makes a packet and say now you go and execute, right. If the compiler actually does this type of a scheduling, then it is called static instruction scheduling. So there are some architectures which we call as VLIW, very long instruction word, very long instruction word. Itanium is one such example of a processor which supported VLIW, where static instruction scheduling is done. In our case, whatever we are going to see now, this entire thing is done dynamically, and for example MIPS embedded processor or ARM embedded processor does have dynamic instruction scheduling, sorry for the spelling typo, and we will learn a technique called Tomasulo's technique. Tomasulo is the name of the scientist who found it. So we will do this Tomasulo technique of constructing an hardware which will do dynamic instruction scheduling, meaning it will be responsible for handling all the data hazards, namely raw, var and WAF. Followed? Yes or no? Before we proceed to this, we will have a very short introduction to static instruction scheduling. Static instruction scheduling is done by the compiler. That is why the word static is there, when the program is not in execution. That is why the word static instruction scheduling. So what will the compiler see? It will take a bunch, so suppose I have k execution units, not all the execution units may be symmetric. So let us go back to this slide. I have k execution units, not every fellow can do integer addition. There can be some 4R5 who will do integer addition, there can be some 4R5 which will do floating point, there can be someone who is doing some SIMD instructions, right. Now the compiler will know what the architecture is. It knows that there are k instruction, k units, and each of this is capable of doing this. Then it will now go after it, after it actually compiles and makes the machine language program. Now it will go and look at this machine language, and then it will machine language program, and it will see if I could assemble k instructions such that there is no data dependency between them, and these k instructions should adhere to the units. So the first instruction, if the first unit is integer, it should be an integer instruction. The second unit, if it is going to be like here, right, if the second unit is going to be a floating point unit, it should be a floating point instruction. Like that, for every unit it will find if there is an instruction that could be executed, it will find, and the k instructions that I am going to send at one shot, none of these instructions should be what? Dependent. There should be no data dependency. So it will make one bundle like this. Obviously it cannot find a bundle where all the instructions are productive. Like I may not find a bundle where I have a floating point and an integer instruction also. So it may not be successful in finding a bundle with k instructions, each matching with the corresponding execution unit, and there is no data dependency. It becomes extremely complex there. Are you able to follow? Right. So what it does, it takes say some r units, r less than k, r instructions it schedules. For the remaining fellows he will put no ops, NOPS, okay. So any instruction set architecture in the world will have something called NOP, no operation, right. Even if you go into the Intel manual, you will find there is something called NOP, no operation. Why do you need such an instruction at all? Why do you need a no op? This is one example. I will show you many more examples, but this is one example. In the case of static instruction scheduling, if I do not find enough instruction to fill all the execution units, for those units corresponding to those units I will put no op. So what is finally what is static instruction? What is static instruction scheduling? I make a very long instruction word to accommodate k instructions, and if I do not get k instructions that such that each instruction adheres to the execution unit and adheres to the execution unit on which it needs to execute, and also that there is no data dependency. If I am not able to get those k instruction or one bundle of k instruction, then I put no ops. Now as you see, the hardware is not complex because the hardware is not going to do the dynamic instruction scheduling. Hardware just takes one bundle, executes it and throws, then next bundle executes it and throws. So the hardware becomes extremely simple, but the compiler has a nightmare. Not a very big nightmare, but it's indeed a nightmare. So that is one very important thing. So what happens is that many times I do not find k instructions in a bundle, so I land up with adding lot of no ops. So the size of the execution the executable program, the final executable program actually becomes very fat. So that is one major drawback of this static instruction schedule. The second important drawback of this static instruction scheduling is the portability of the code from one architecture to another architecture. Tomorrow if I put k plus 1 execution units or 2k execution units, then this executable will not run on that. So I have to go take back from the machine code again, I have to do bundling again, right. So the portability is going to be a major issue right, and many times what happens is that they use some software firmware emulator to handle this portability issue. I move from a core which had earlier k execution unit to k plus 2 execution unit, then every bundle that I have generated should have either 2 no ops or it needs to be rearranged. So I can't basically every time a new a new VLIW architecture is announced, even in the same series, I can't go and keep on compiling new versions and say for this you use this version, then it becomes commercially unviable. So that was one major drawback in this static instruction scheduling. There were some software firmware emulation solution which basically did not work that effectively. Today we do not see many of these VLIW machines, so I will not put lot of time on trying to see their architecture, but basically we will have at an introductory course of this nature, we will have an introduction. Okay. Now there is something much more complex that happens in static instruction scheduling, and that is this. This problem what I am going to describe now is called memory aliasing, okay. And this is something which your static instruction scheduling cannot handle, okay. Now what is happening here? Let us carefully look into this. Now I am trying to store a value of store the value of R2 onto the address R1 plus 20, and I am reading the value of R4 plus 40 and storing it in L3. So I am writing into R1 plus 20 and I am reading from R4 plus 40. For some reason if R1 plus 20 is equal to R4 plus 40, note that this is a raw hazard, and this hazard the compiler cannot detect. Why the compiler cannot detect? Because at the time of compilation it does not know what is the value of R1 and what is the value of R4, correct. This is going to be dynamically determined, right. So if I see a load and store a load following a store, it can potentially be a read after write if those two addresses become the same. This is called the memory aliasing problem. What they say, let R1 plus 20 be 100, so 100 can be approached as R1 plus 20 alias R4 plus 40, both will give me 100, but this I cannot find out at the time of compilation. Are you getting this? So, since I cannot find out at the time of compilation, if I see a load and store typically like this, what will happen? The architecture has to schedule it one after another. So, they can't put it in the same bundle. I can't put a load and store even though there may be no connection at all. See, this is using some R1 R2 register, this is using R3 R4 register. There is absolutely no connection, right, as in the prima facie view. Statically if I look at these two instructions, I do not find any connection. Dynamically they could land up, right, if R1 plus 20 equal to R4 plus 40, which I cannot find out at the time of compilation. So, when I have a load and store such that load follows store, then better I put them in two different packets. That means if there are a lot of instructions that are dependent upon this store and load, those cannot be packed together here. So, load store essentially becomes sequentialized and that is very important about static instruction scheduling. This is a thorn in the flesh and you will see lot of load and store in your program, because ultimately you have to read from the memory for every variable and write back to the memory. So, when you see lot of load and store together, this is not by the static instruction schedule. If I am going to do static instruction scheduling, these should happen one after another. Now, what we will be covering in our thing is a dynamic instruction scheduling, wherein the data hazards are handled by the hardware, right, they are not handled by the software. So, the memory aliasing type of issues will all be handled by hardware, and that is why the hardware becomes a little more complex. Okay. Now, there are two types of data hazards. So, we will have something called a raw hazard. The raw hazard is basically solved using the operand forwarding technique. Okay. Operand forwarding technique, while the var and vav hazard will be solved using something called register renaming technique. Okay. So, these two techniques we have to implement it in hardware and show that it is working, correct. Now, also understand this raw, we will see that it is actually a dependency, it is a true dependency, while this var and vav are not, are virtual dependencies or whatever you call it as named dependencies. You can even call as false dependencies. Okay. We will show you why. Okay. So, the hardware that we are going to deal with in tomorrow's class, right, is one that will solve the raw and var and vav hazard completely. We will spend 45 minutes to understand this. For the raw, we will be using something called an operand forwarding technique, while for the var and vav, we will be using something called register renaming technique. So, in literature of computer architecture, there are two things, one is true dependency, another is named dependency. In true dependency, there is actually a dependency, and I cannot solve the true dependency problem by any means, I have to wait, right. So, if there is if the previous instruction is holding the data that I need, I have to wait for it to complete. So, that is why we call it as a true dependency. We will elaborate that a little more tomorrow. While the var and vav are virtual dependencies, if I go and do some jugglery, then these things will disappear, your var and vav can disappear. We will use something called register renaming technique to do that. Both these together we will cover in tomorrow's class. Okay.